spectrometers. Gas phase and liquid phase, so real quickly, that column with that 30 meter, it goes into an oven, we inject it, it gets out of the column, a gas pushes it through till we get to the mass spec, and we can do the analysis. In the same way, we can connect it to a liquid chromatograph, and here we have two different solutions. A is common or water-based, B is organic. You have some nice pumps to push it through the column. Again, the smaller the particles, the nicer the separation. But my engineers over here will tell you that as we get smaller particles, we have to have a higher pressure pump. And so one of the big issues today is how well can we make those pumps to get the solution pushed through the smaller particles. What does that mean for us as far as hazardous waste? I live in San Diego, California, way down here in the United States next to Mexico. Beautiful place, but it's a desert, not much water, but it's perfect conditions, almost like it is here for growing. And it's known as the winter vegetable grower for America. There's a grower out there who he wants to grow organic spinach. He has a fish emulsion that he puts into the water, and you can see the little spray heads come out on this spinach field. And what he does then is he's got acres and acres and acres, probably 10,000 acres of spinach. All these people aren't thinking. The field next to him, a gentleman was growing alfalfa for cows. He had a lot of weeds. What does he do? He sprays 2,4-D and dicamba. He dripped it. That's what the spinach now looks like. Organic spinach. And so even the small spinach growing up was affected. And so what I want to show you is that then we can take a mass spec, we can look for those compounds, and here we see 153 parts per billion of the 2,4-D and 54 parts per billion of dicamba. So this is what we use the mass spec for, maybe to keep your food safe. A little closer to home. What's our spinach problem in San Diego? If we look at particulates, in this case they will look at endocrine disruptors and polynuclear aromatic hydrocarbons. Endocrine disruptors, bisteral hexylphthalate, dioctophthalate, chemicals that we put into plastic to make sure that they stay soft and subtle. So the issue was that we want to look at these things on PM 2.5 particles. Those are ones that get deep into the lung. And he used a triple quadrupole on this, and he took his quartz filters, the simple, very simple preparation. He extracted it with hexane for 30 minutes, blew it down, and he separated it with water, organic solution. Here's his results. You can see that he had on some of these, not so much, quite a bit. He had developed this so he could look at the cancer capabilities, and we saw that for the polynuclear, there we go, perfect. But for the phthalates, it was below the US threshold. If we looked at the polynuclear aromatic hydrocarbons, it was above the thresholds. And the takeaway here is that originally all these were done by a GC mass spec, a gas phase. But by going to a liquid phase, he was able to get the work done faster and more efficiently with a simpler sample prep. If we look at another test, we can see that we can also analyze metals. And you can use a flame atomic absorption. And here we're looking at the emission absorption because on any element, the electrons can jump to a higher orbital with specific energies. And we can have a specific cathode, which tells us what those are, and that gives us a capability of parts per billion or parts per million analysis. But we waste a lot of the sample trying to get it into an aerosol, and all the elements don't absorb in the flame. Let's get rid of the flame. We'll put it into a little tube where all the sample is used, all the sample is in the light path. This is a tube, and then we put a very high voltage source around it to get it hot here to 3,000 degrees, and then go for parts per million to parts per billion capabilities. And we can get it to an ICP, and here we use light, and just like a camera, we can end up taking the light, very similar to the camera with a chip, and we get a picture of all the elements that can be seen. But I showed you that front end of the torch. So this is that cone, and we've got that 10,000 degree, and here we want to sample the masses and look at the masses directly. This is it in the instrument. We've got two cones, and if we look at the insides, but what's more important is that if we look at the ICP optical, that you have a massive number of jumps an electron can have. But if we look at the mass spec, vanadium gives one mass of 51. It looks something like this. We talked about the isotopes, cadmium isotopes, antimony, 2 isotopes. So, how do we look at these in reality? Up in the town that's southwest of here, they're looking at the heavy metals in their food source. Arsenic is accumulated in rice. You know that mercury is in fish. So the main sources are rice and fish. And they want to look at, do we have any differences between the age, male and female, if you're vegetarian or not? Analyze it by ICP-MS. And in the blood, they're looking at it that there's a little bit more arsenic decrease as you got older. Lead, mercury, almost no correlation. Gender, a little bit higher lead in males, and so forth. But when we looked at the food, essentially, everything was below the World Health Organization guidelines. Yeah, arsenic in rice maybe a little bit higher, but essentially, the study had no real significant finding. If we go to a site in northern India, so these are PM10s. These are bigger particles that you might get caught in your nose or in your esophagus. And they're looking at certain metals because they're the tire and brake wear metals, also some from the road dust. And they want to see how much higher cancer rate are these causing. We can classify the metals as either carcinogenic, probably carcinogenic, maybe it's going to give us cancer, or it pretty much doesn't give cancer at all. And what we found is that the total amount of material on these PM10s is much higher than the World Health Organization standard. And if we look at it, everything, interesting, everything but lead. Why is lead lower? 2000, India removed lead from gasoline. So even though the World Health Organization, or in this case the Indian air quality standards, allowed 500, the level in this town was now 205, so much lower. So this is where something where the government had mandated change, which had a direct effect on the health of the people. And they correlated this to the increase of different elements compared to the natural background. So, the issue is here, is we've got a problem. This is northern India. What about here? So my question is, we have civil engineering students here. You're going to be designing roads. You're going to be designing infrastructure. What are you going to do to eliminate this problem here in Bengaluru?
Thank you for the presentation. Okay. Do you know that I had to walk to the back to ask any questions. Do you know why? All the noise comes from the back. So it looks like they have no control. When I'm sitting there, I can hear the backbenchers making noise. That affects all of you sitting in the front, may not be able to hear the presentation if the back rows make noise. So one of the ways in which I would like to understand whether the backbenchers understand anything about what's being said is to ask some questions, right? Okay, let me pick somebody. Now everybody is quiet, right? I'm looking. Okay, if you are like this throughout the presentation, it helps everybody and you are likely to learn something before you go home. So I may be asking people questions not to embarrass you. I just want to make sure you get something and you take something home. Okay, that's my intention. I'm not here to embarrass you. Okay, let me ask the middle person. So tell me, the question is, oh, your faculty. So sorry about that. I missed it. You are exempt. She is exempt from answering any questions because she knows everything. She is on the faculty. Okay. Sorry. No. I want to pick some students. Okay. I would like to ask this gentleman who is looking on the other side, 1, 2, 3, 4 from here. Yes, please stand. Yeah. Okay. Okay, it does not mean that you have to make noise. You need to listen to what he says. Okay? Okay. Who was the speaker? And what did he say? What is the name of the speaker? And what did he say? If you don't know, tell me.
Richard Phillips.
Richard Phillips, that's correct. What did he say?
About hazardous waste. Hazardous
waste. That may not be close to the correct answer. Not even close. But he said something different from, in addition to saying hazardous waste. What did he do with the hazardous waste? What did he do? He spent about 40 minutes, right? He spent about 40 minutes. So I expected all of you to hear what he said. Remember, in the beginning of the day, I said, whatever we are doing is only for you, not for me, or not for us, but for all of you. So, the answer is, the first one is correct, but the second one, unfortunately, is not correct. Okay? So please sit down. I want to make sure some individuals at least learn something from what is your faculty, Napa. You really, please stand. The mic kodiyappa. Yeah, please don't make any noise. The last one. When you talk slowly. Otherwise you will be making noise. Please. Who? He already said who spoke today. What did he speak about?
Sir, he speak about the different materials that are causing the hazardous, which like heavy metals and some the other materials which are affecting our being. So he spoke about the materials and the instruments that are related.
Right. Instruments.
Yes, sir.
Instruments is the key. He talked about a number of instruments that can be used to analyze hazardous materials. Okay? That's good. Does anybody want to give him a memento? Okay, please. Ikkada Baba. On the mic toward.
So congratulations. You are from which college?
Avi College of Engineering. Yeah. I'm Amar N. Gupta from Avi College of Engineering, 3rd year Civil Department.
Okay. Please remember, we are not giving any incentives for you. We are only giving a memento to recognize those individuals who are actually listening to the presentations. So I encourage everyone to continue that. Otherwise, I will come back at you and ask you the questions to know whether you have learned anything or not. Next speaker, please.
Ms. Robin K. Spencer is the Environmental Specialist for the West Region of Sims Metal Limited, the global leader in metals recycling. Ma'am has received her BA in Geography from the University of California, Berkeley, a certificate in Hazardous Materials Management from the University of California, Davis, and an executive certificate in Sustainable Management from the Presidio Graduate School in San Francisco. Ma'am was a founder of and served 4 terms as President of the Northern California chapter of the Alliance for Hazardous Materials Professions, 2 terms as a Director at Large for the National AHMP, and 2 terms as Director at Large for the IHMM, completing her service as Vice Chair of the Executive Committee. Ma'am is honored to be a member of the 2014 AHMP delegation to Bangalore and Bhopal. Welcome you, ma'am.
Good morning. I'm glad to be speaker in the morning while you're still fresh. I want to thank Richard for his excellent explanation of the chemistry behind the scenes. What I'm talking about today are select hazardous waste processes, treatments, technologies, and recovery. So what he does and the labs do is all behind the scenes. I feel that I do the easy part, like collecting samples, packaging them up, sending them to the lab, and 2 weeks later I get information that we can further use. So thank you for all you do, and Brendan. So we'll talk about the principles of hazardous waste management, handling and storage, selecting appropriate technology, and we'll look at wastewater, land disposal, and just wrap it up with a mention about testing and record keeping. As you know from listening the past 2 days and this morning, that we have gone over all of these topics, all of our delegation, and so we're wrapping it up so you see the whole package of what a hazardous materials manager does. Again, definition of a hazardous waste. This is pretty standard. Any waste by reason of any of its physical, chemical, reactive, toxic, flammable, explosive, or corrosive characteristics causes danger or is likely to endanger health or environment, whether alone or when in contact with other waste or substances. But yesterday, I gave a better definition, the one I feel speaks more clearly to everyone I work with, and it's this: a hazardous material which can no longer be used for its intended purpose. A little asterisk here, it's up to the generator to decide when a waste is a waste. So your hazardous material can be useful, and then when you decide you're not going to use it anymore because it's spent oil, maybe something fell on the ground, you cleaned it up, now it's a hazardous waste. When you're working in a company, manufacturing company, you'll have waste. Will be liquid, water, sludge, oil, used chemicals. Again, think about your laboratory shelf where you do your analytics, and chemicals have a shelf life. So when they expire, they need to be sent off as a hazardous waste. So how do we do this? We do analytical testing. We use our safety data sheets. We get a lot of information that, but we can also use our own knowledge and say, well, oil on the soil, we're going to have to get rid of it in California as a hazardous waste. We'll talk about waste management principles, and then you need to look at the best options for handling this waste. Maybe it's treatment, and while you're waiting for answers, you're storing it, and that's what we'll talk about pretty soon. So the waste management principles, one, we want to minimize waste. You want to prevent it. You want to use small amounts. Don't get a great big bottle of acetone and pour it on whatever you're cleaning. Put it on a rag and use it. You want to minimize reuse waste materials as best you can. In California, oil is a hazardous material, so when it spills on the ground and we pick it up with an absorbent, it's now a hazardous waste. A lot of people who are untrained will put a whole bag of sand or absorbent on a small puddle, but that can be reused, and you put it into another drum, and you just reuse it, saves you money, and it's better for the bottom line. We can also recover waste materials, recycle waste, remediate, use treatment. We can use it for energy recovery. So if it's gasoline, if it's oil, that can be reprocessed. Finally, the last option is disposal. Sometimes that's the only option. We have this type of triangle. The desirability is up at the top, where we prevent, then minimize, reuse, repurpose, recycle, and recover, remediate, treat, and again, the last option is disposal. I'm just going to talk a bit about handling and storage of waste containers. It's pretty much the same as a hazardous material, but there's labeling involved. There's the employee right to know and the public right to know that you have hazardous characteristics. First, you want to make sure that you are storing compatible chemicals with others. You need to decide the size of your container. It could be a drum, it could be a bin, it could be a tank. When you have these closed containers, you have to consider expansion, the temperature, pressure, phase changes, and reactions. It's critical, as you can imagine, that the drums be kept in good condition. All the seals on tightly. You keep them closed when you're not using it. If you have a liquid, you can use a funnel to pour it in. But you also need to label and identify the contents. We talked about hazard communication. It's critical. We have an OSHA law, is if you have a bulk container and you remove something from it for use, then you must have the name of the chemical, the manufacturer, and the physical or environmental hazards. If it is used by anyone other than you, it has a possibility. If it's only used on your shift, you don't have to label it. But if it's used on the next shift, or if you're going to have it there overnight, then you must label it. Flammables need to be bonded and ground. If you have fume hoods, use that. Have good ventilation. And of course, wear the proper PPE. Accumulation areas. In the U.S., and perhaps in India, I don't know, we have to separate the waste from others. Only authorized personnel can be in that area. It's part of the security program. Liquids need secondary containment, weekly inspections. Tanks with waste need to be inspected daily. And we have accumulation time limits, so we don't have a big warehouse full of drums. Every 90 days, they need to be shipped off in general. So let's talk about treatment. Yesterday we talked about recycling and resource recovery, reuse, but now we're at treatment, and this is what we can do. Treatment is a process changing the physical, chemical, biological characteristics of the waste to render it less harmful. It's applied to waste before disposal. And these are some of the treatment activities. Neutralizing, treating with acid or a base. Recovering the energy or material resources. Making the waste less hazardous, and making it safe for transport, storage, and disposal. Okay, you need to consider who can undertake the technology assessment. Do you need a chemical engineer? Do you need to hire a consultant? Do you need specialists? Or can the in-house operations or maintenance people say, well, we just need to change the pH and it'll be fine? Or do you need a permit from the regulatory agency? What wastes are acceptable? Transport. We had a good discussion about the limits of transportation and the hazards involved with that. How do we monitor it? Who will design the treatment plant and train the operators? Oftentimes, your company will not have that specialty and will either send the waste to a treatment center or build a plant on site with the help of specialists. Key questions. Is it simple? Sophisticated? How are we going to make sure it is running correctly? Do we have maintenance? Are there any environmental impacts? Is there air escaping? Is there water that is part of the treatment process that you also need to look at? And again, permitting. Workplace hazards. I won't go into that. We know that they exist at all times. Waste reduction, avoidance, waste minimization. This is key to creating an environment of small waste generation, reducing the amount of waste on site, reducing the hazards involved, and reducing the costs. A lot of times the treatment processes have residue. There might be ash. There might be soil that has been treated in some way to encapsulate metals. What are we going to do with that? Do we test it? Do we see if it's still hazardous? Absolutely. If it's not, it can go into an easier landfill, not a hazardous waste landfill. It can be used as alternative daily cover if we're lucky, and the cost is much reduced. Okay. Key factors. You need to look at the chemical properties through analysis. Composition, concentration, acidity, oxidation reduction potential, solubility. A lot of factors go into this, and this is why I love chemical engineers, because they have great solutions and help us a lot in this industry. Physical properties considered. Can you put binders, like I spoke yesterday, where the scrap treated shredder waste, the rubbers, the plastic, the glasses, we encapsulate it or treat it with cement and silicate to bind the metals in there, metals and PCBs, so they don't leach. So we have physical, chemical, biological, thermal destruction, metals recovery, solidification, stabilization. These are key treatment technologies. Treatment. The key is volume reduction. We try and concentrate it. We can destroy it. Isolate the hazardous materials. Convert hazardous to non-hazardous substances. And then finally contain it in a smaller quantity, again to reduce cost and the hazard. These are some methods. I'm not going to go through them all, but it's all physical, mechanical. Some are phase change systems. You can do, if you have volatiles in water, you can do air and steam stripping of the volatiles with these type of systems. You can have biofiltration, where water enters, this is packed media, usually activated carbon, maybe some zeolites and other materials to remove metals. Chemical treatment. Transforms waste into less hazardous substances. I do a lot of stormwater pollution prevention. And one of the big treatment systems we have is a natural system like this on top, where we have biological systems that are reducing the waste or taking it up in the soil, and then in the dry season we'll scrape off the soil, clean it up, and remove that. Biological treatment uses microorganisms. It degrades organic compounds in the waste stream. Reduction and oxidation, with oxidizing reagents, reducing. So this is where chemistry comes in. This is one of our projects. where we have cutting oil that comes in on water. In the metals industry, where there's shavings created from the manufacture of parts, water and cutting oil is absorbed onto the shavings. It piles the piles. It's just dripping wet. So what do? When you squeeze it into a block for recycling, all that water comes out. It's oily. So it comes in, or a water tank goes through a treatment with various chemicals, lime, polymers, ferric acid. We raise the pH, then we drop the pH. Comes through flocculant, winds through the system, treated with zeolite and a carbon filter, and then is discharged to the sanitary sewer. We're getting rid of about 4,000 gallons of treated wastewater every week. If you can imagine having to pump that out with a tanker truck and shipping it to another treatment plant, it would be very costly. Biological treatment. Excuse me, at the back. Hello? Do you want Dr. to ask you to be silent? Biological treatment uses natural processes, ubiquitous microorganisms, just native bacteria, fungi can work on this. This is used often for low contaminant concentration organic waste, like Hazardous in your water treatment plants. pH has a big deal, physical form of the waste, and again, it's for organic waste with relatively low toxicity. We use activated sludge, aerated lagoons, stabilization ponds, use anaerobic digestion. A lot of this is waste, like in the water treatment plants. Thermal destruction. We have a picture here of a commercial boiler where the waste is fed in with water, high heat, and the material is actually incinerated. The thermal technologies offer opportunity for energy and heat recovery. So it can be used to power, it can be used to heat buildings, and high BTU waste can be used as fuel, which gives you the opportunity to reduce your consumption of fresh fuels. Industrial furnaces, cement kilns. This is where a lot of waste goes in our country, into cement kilns for the energy recovery. Lime kilns, other kilns, coke ovens, blast furnace, and other furnaces use the recovered energy products. Okay. Here's another example of a combustion chamber. The air is fed in, waste liquids, extra fuel. The waste is here. It's heated up to 1200 degrees centigrade. Comes through the secondary combustion chamber. Particles go through the baghouse. And at the very end, you have ash. And that's your hazardous waste. So you've gone from a large volume to small volumes. Metals recovery. We can separate metals from other constituents of waste through filtration, ion exchange, reverse osmosis, and others. Energy recovery is one of the primary benefits of a lot of our waste to energy. There's heat exchange, we can produce steam, electricity is generated, and the sale of surplus energy improves your bottom line. Solvent recovery is also affected by heat. The solvents are volatilized, removed, and recycled. Stabilization is yet another, kind of like our alternative daily cover from the recycling treated waste. And we encapsulate the waste into the product that is shipped out using cement, silicate. Otherwise, if you have very toxic forms, you can put it into a container, cement it, or use other materials just to solidify it, encapsulate it, when it goes to the landfill. Converts waste into insoluble rock-like materials. Hopefully, that's recommended for inorganic waste and often is used before disposal to landfill. Stabilization has to do with chemical reactions. This is an older model of a cement-based solidification system. The waste is fed in, the cement is added, and it comes out treated. It's known, depending on your waste, what is the best way of disposal. Here, landfill for non-toxic inorganics is about the only solution. Wastewater treatment process. You have pre-treatment, can be done on site, treatment through aerobic, anaerobic methods, filters, and discharge clean effluent. As you know, wastewater treatment processes have all these various stages, and usually there are discharge limits that we need to adhere to. And if our water does not meet it, it's just pumped back into the process until it does. Landfills. This is a problem everywhere. If you don't have a prepared landfill, which is lined, has some sort of leachate collection system or methane collection system, you're going to have waste leaving the landfill, either into the soil, into the air, into the groundwater, and then that leads to runoff, and it can go downstream. There can be uncontrolled burning. You don't have little individual cells at the landfills. It attracts flies, vermin, other insects, it's dust, odors, and when people are scavenging, if it's open to that, it causes harm to human health, the landscape, and can result in explosions and fires. So what do? Here at the bottom we have an open dump where there's no controls. If you have a designated area, dumping is kept in this designated area. It's away from residential areas, and so the vermin, the insects, scavengers, are in one place. Semi-controlled landfill, this is where it's supervised. There's some regulation. There's an acceptance policy of waste. And they cover the waste. The highest level is the sanitary landfill, industrial waste landfill, where engineering and operation and control measures are in place, and there is great regulatory oversight. This is a typical industrial waste landfill where the waste is in blue. We have a liner that comes through. There are leachate collection systems. There are methane collection systems. It's located where it's protected from the groundwater, and it's well controlled. The last item, testing and record keeping. When you're doing your waste analysis, you need to keep that record. When you're doing your treatment, you need to keep the records. You need to be able to prove that you handled the waste correctly, legally, and responsibly. As we've learned in other presentations, waste is a cradle to grave responsibility, and the generator will always own it. So you want to be sure that it's sent to the right place and treated. Records will provide details of transfers, the landfill, the regulations required, when it was sent there, and the exact location in the site. And so, a brief summary went over principles of waste management, handling and storage of waste, making sure there's good signage, labels. We talked about various technologies. We looked at wastewater, land disposal, and I just want to leave you with record keeping is critical. Thank you very much.
Thank you, ma'am, for a wonderful speech. Since 1990, Mr. West has been president of BA West Associates Incorporated, an engineering and consulting services firm focused on the assessment, design and management of property-related environmental issues. Mr. West has over 43 years of experience managing, operating and developing engineering, consulting and cleanup contracting businesses for several national and international corporations. Sir has received his bachelor's degree in chemistry from University of Cincinnati and studied graduate level analytical chemistry at Rutgers University. Mr. West received his certification in 1992 and is a CHMM. He is also a fellow and distinguished diplomat of the Institute of Hazardous Materials Management. Welcome you, sir.
Excellent, thank you. Good morning. Great to see so many of you here. Before I get started, I'd like to just ask a quick question. How many people here are involved in biology? This group here. Okay, very good. How many people are chemists or in chemistry? Oh, we got a few. All right, very good. How many people are in engineering? Ah, yes, there we go. How many people are in computer science? Okay, very good. Thank you. Thank you. Gives me an idea of what the audience is. Thank you. So we're going to talk a little bit today about impacts of mismanagement of hazardous materials. And this presentation is driven... Oh, management people. Okay, oh yeah. How many in management? Ah, there we go. Excellent. Thank you. Dr. Shank, thank you. Very good. So, this will be driven primarily by examples. They're at the end of the presentation. But up front, we're going to talk about resources that can be used in various stages of handling hazardous materials. So what's important is we handle things safely. We handle things without injury or impact to the environment or humans, other human beings. So the agenda includes steps for handling hazardous materials, the resources that address each, what we can do and what can happen, and what has gone wrong. So those are the history lessons. And the examples of the resultant damage, injury, and we'll talk about how to avoid some of the instances as well. I think we'll also use the recent example in HARDA. So, how do we interface with hazardous materials? Well, if you're in a production facility making it, we're obviously handling materials that are hazardous. We're making things that might possibly be hazardous. So production is a key process part of handling hazardous materials. The packaging, after it's made, after products have been manufactured, it needs to go into a package that's capable of shipping it across the country without damage or release. The shipment, the actual movement of a packaged good from point of storage to the consuming point. That transportation has a set of regulations with it and a set of practices with it that's required to be followed. And then we receive it, we store it. How do we put it into a storage facility? This can be applicable to both hazardous materials as well as hazardous waste. You'll see that in the next part of the presentation here. We'll use the materials. We'll use hazardous materials in the production now. We're going back into the production process. That process will generate waste. We'll talk about the packaging, storage, and shipment, and then disposal. You see these elements are common among all of our presentations. It's a reinforcing of what we've been talking about, but now we're going to talk about real-world instances where things did go wrong and what we can do to avoid them. So, in the production facility, we have access to production documentation. Somebody made the process. Somebody built the reactors. They know what can go wrong. They know what the safety measures need to be. Look for that documentation. Safety data sheets. That's going to be a thread throughout this presentation. The manufacturer has put into a few pages exactly what you need to know to touch, handle, express this material in whatever fashion you need to do so. The facility itself oftentimes has its own safety protocols. Each manufacturer, like we talked about GE for quite a while the other day, they all have standard protocols that they've drafted themselves. Get those. If you're dealing with a product that it's in your facility, get those procedures because you need to understand what your company is telling you should do. Then drills. If you're in a manufacturing facility and safety drills are done on a routine basis, we talked the other day, Stephen talked about How often should we be looking at risk assessments? Well, those risk assessments fall into a category of planning. The planning then turns into drills. The drills are the things that we practice on a routine basis to make sure we know what we're doing if something happens. We have daily safety meetings as well, and the post-incident analysis if we actually have something happen to it, if there is a process problem. So in packaging, once again, we're talking about material safety data sheets or safety data sheets. Any manufacturer provided information is where you start in this planning process. So there's a series of international regulations. I didn't get China on here. That actually has its own set of regulations as well. But now it's sort of being globalized, and you're very close to accepting the globalized, the harmonized system. The shipment, once again, we're talking about shipping regulations and the standard practices of international organizations like the Air Transport Association or EU rules. Even within the countries of EU, you'll see a change for ground transport from one to the other. And that was covered the other day. And then the customs regulations associated with them. So receipt and storage, got to put it in the right spot. If we don't put it in the right spot, what will happen? Somebody will hit it, will impact it, will create a problem that results in an accident. So put it in the correct location. Don't store it with incompatible materials. Make sure the labels are attached to the package understandable, readable. Oftentimes they get marred, scarred, or otherwise mishandled. And then I've listed a couple of agencies in the U.S., but clearly India is developing its own set. It's basically adopting a lot of what the world has accepted. In use, facility operations, that's the key. Talk to your managers, talk to people that are actually designing the processes that you're going to be involved in, or your own managers. Look for plans, the process plans. If you have a plan that lays out what materials go in at the beginning of the process and what comes out at the end, look at all the intermediate steps and see if you can see a potential problem, a potential pressure point. Look at audits. Smart people come through every once in a while. Stephen talked about it. Just to make sure that what is being done conforms with what our standard practices for your process or your organization. Process safety plans, health and safety plans. Health and safety plans, very individual for the process, very individual for the workers involved. So you want to make sure you understand those plans. Have them on site, have them handy. Waste packaging, very much the same as transport, is being adopted slowly, surely here. So let's get into some examples. But before we do that, let's talk a little about Garda. The explosion that happened yesterday and killed 11 people, we don't know what happened exactly, but it was an explosives operation. So clearly a cracker operation. Clearly there was a hazard that was known before the incident happened. It was severe. It burned the place to the ground. Individuals were hurt. 174 individuals, 200 transports to the hospital. We also had 11 deaths. What I found interesting in reading the article associated with it was most of those deaths were people that were observing the fire, not plant people, not necessarily plant people, not people associated with the process. That particular note really is concerning. Incident command requires you be able to control the area around the incident. That incident command structure that Kendra talked about needed to keep those people away. That exposure is truly unacceptable. So this first instance, let's go back to this. This is a project I did in 1990, so a long time ago, 34 years ago. It was a standard office building that had fire plans, it had exit points, it knew exactly, the building's management knew exactly where their people worked and what they did. It was a high-end structure, Class A structure in the U.S. On the weekend, a service group came in to refinish wood doors, wood paneling. They were using a linseed oil finish. They put the rags from that finish, their waste, into a plastic container. They sat it at the window edge under the sunlight and left for the day. Over the weekend, those linseed soaked oil rags auto-ignited. The degradation from UV regulation resulted in a fire. That wasn't the worst of it, because that probably could have been controlled. It should have been sprinklered well enough. It wasn't. This 38-story mid-rise structure, you see an outlay over here. The fire started on the 20th floor. It was sprinklered further up, like the 30th floor. It was not sprinklered at 20. Planning instances there we can talk about for a long, long time. But what happened was the burning process burned down light ballasts in fluorescent lights. There were 200 lights per floor. It burned for 10 floors. These ballasts are very small to reasonably large and contain a wax in the capacitor that lights off the light. That wax contained PCBs. Manufacture of fluorescent ballasts contained PCBs for a long, long time, even after this particular instance. The process of burning the PCBs was high enough that we had dioxins and furans form. So now we have a building that's burning 10 floors into the structure. We have steel I-beams that are 18 inches in web size, and they're deflecting 6 to 10 feet. So now the structure is failing. It's actually melting, if you will, while we're getting contamination on the outside of the building and the inside of the building. When the firefighters come to fight the fire, they have to do it from an adjacent building because they can't get up the stairwells. They can't access from the top. So they fight the fire by putting water on it, which finds its way down through the primary conduits of the structure. The stairwells, the elevators. Those happen to be built at about the time that the U.S. government said you can no longer use asbestos in these areas. So we found that asbestos, when we did the assessment, was slowly, as the building rose, slowly being eliminated from the floor areas, but concentrating in the riser areas, the areas of piping, elevator, and the stairwells. Those were the hazards we faced once we found out what happened. But that fire burned for 6 days. This structure eventually had to be taken down piece by piece because the remaining contamination from PCBs and dioxins on the surfaces was so ubiquitous as to make it too costly to keep the building. That's an unintended consequence. Auto-ignition is not something that's easily predictable. But if you have a contractor that's using linseed oil, that's controllable. When they come to your site, understand what the materials are that they're going to use and where they're going to use it, and make sure that they take out everything that they're using on a given day and not leave it over a longer period of time, 2 or 3 days per weekend. So this instance was smaller, much smaller, but it was in a waste cage in a facility that produced a lot of chlorine-based products, bleaches, cleaning products. Those materials were stored as waste in this waste cage in a mixed form because they came out of research areas, laboratories. So oftentimes they were smaller containers, larger containers, 5 gallons, 10 gallons, 20 gallons. Okay, thank you. Those containers were then consolidated by a contractor who came to the waste cage and poured them together. The debate is whether that was actually treatment. The process of pouring them together, though, oftentimes took things that were basic, peroxides, and things that were basic being the bleaches and the hydroxides with that, and peroxides which were more acidic. Slowly, when they mix, they create a heat. That heat impacted a 1H1 drum, a polyethylene drum that this mixing was being done in. It was rated for 120 degrees Fahrenheit. That heat easily exceeded 120 degrees Fahrenheit. What we proved is about 140 to 150 degrees Fahrenheit. The result was that the drum weakened. The sidewall of the drum thinned. The 3 to 8 millimeter wall, either the top or the side, eventually bulged. And a worker who came to move that drum to a transport vehicle put it on a dolly, and when he rocked it back, that weakened wall of the drum literally failed. Now, he was splashed. The whole area was splashed. When the firefighters arrived, they didn't know what that was. There's water everywhere. That's what it was, but the neutralized materials. The downside is that it scared him. So simple. It scared him because there was this sudden whoosh. All of the fluid lands on him. He fell backwards, and the resulting injury was because he hit a steel rack. He hit his head on the steel rack, hit his pelvis, was impacted by the falling drum, and there was plenty of guilt to go around. This lasted through a couple of iterations of litigation. Very simple thing to do. Don't allow the mixing operation on your site. But have that SOP in place. Write that plan, put it out there, get your contractor to agree to it, make sure you monitor what he's doing so that you don't wind up with an out-of-control situation that could have been easily prevented. Interesting one, project from the late 90s. Oftentimes, hazardous materials can be stored in 55-gallon steel drums, but when you go to consolidate them into something larger, you really don't want to spend a lot of time taking them apart. So some things wind up going to a shredding operation. This is a waste handler in Michigan that had a drum shredding operation in which he supposedly screened everything coming into him, had a permit to do the shredding, wound up with a metal separator at the end that could take the steel out, and a waste stream that was treated and landfilled. The residuals were just as Robin said, the residuals were landfilled. One day, he didn't screen well enough for the inbound materials, and he had a compressed gas cylinder inside one of the drums. That cylinder, when it was shredded, did not break apart, but the control valve broke off. As soon as that happened, it's inside a contained area where the shredding operation is happening, it began to release its contents. Contents were flammable. The teeth of the shredder were not made of metals that reduced the incidence of spark. A fire ensued. The operator standing next to the shredder feeding it was injured because the pressure, the back pressure of the explosion resulted in them being injured by virtue of that blast. The facility was burned, and obviously the lawsuit started. What could have been done differently here? That's more vigilant QC. Whatever comes into your plant, whatever your process is, make sure you know exactly what's in that drum or in that container before you actually let it on the site. This is a recent one at a research lab that had been abandoned in the Midwest in the US. The lab had a series of columns that, like Richard was talking about, HPLC columns, and they used acetone in the process. So there was a glass container of acetone, clear glass, that sat on top of an HPLC machine for 8 years. The downside of improper storage and 8 years of no monitoring. That's what happened here. Now, a technician was asked to clean up the lab. He arrived, he had level D on, level D protection. His gloves were rubber gloves. He picked up the container. Now, what happens, and it's a really odd situation, but this is another instance you need to understand so you can think about and protect against the resulting operation. So the container exploded. Now, the forensics afterwards really taught us the chemistry of what happened. The acetone itself was exposed to an oxygen-containing atmosphere under a UV light, and essentially this equation forming, it's the IPA, it was actually in it. The acetone is formed from the IPE degradation, and we wind up with a peroxide that has the ability to explode. It wasn't a lot, it was small crystals. The crystals were at the top of the container. Obviously, when he picked it up, rocked the container, it blew up. So we have isopropyl alcohol, oxygen exposure, UV changes to an acetone peroxide, and then TATP, which is triacetone triperoxide, also known as the Devil's Brew. It's used as an explosive in terrorist operations. The injuries from this particular event, he fortunately had glasses. He had safety glasses on, so his eyes were not affected, but he had all kinds of lacerations around his face and around his arms, and his right hand was so impacted as to have surgery for 3 days to reconstruct. He's now recovering. He survived. That should never have happened to start with. First of all, the lab being abandoned for 8 years is just an impossible situation. The container being outside the hood and the exposure that it was in, not standard operating procedure. That particular instance results in an injury that was recoverable, but easily could have been fatal. Last instance here. This one we've talked about already. Other people have pointed it out. It happened last year in East Palestine, Ohio. There'll be lots of discussion about this for a long period of time. Railroad cars in a train that was about 3 kilometers long. There were 11 cars of hazardous materials. They included glycols, acrylates, and isobutylene, in addition to vinyl chloride. Vinyl chloride being the worst of the actors. This train was moving from St. Louis to the East Coast. So Midwest to East Coast, it's traveling something in the range of 1,000 miles. And just outside of East Palestine, Ohio, the cameras, the closed caption cameras, caught sparks coming off the carriages of the railroad tankers. There was failure in that undercarriage. Lack of maintenance. Those kinds of instances happen frequently, but can easily be prevented with maintenance. Just being sure that you monitor the brake conditions, you make sure the carriage is lubricated, make sure it's attached properly to the vehicle. The derailment happened early February. There was 2 days of burning, and there was interviews about why should we allow this thing to continue to burn during that 2-day period, because there was air impacts. There are 4,700 people in this town. They had to be evacuated. Their houses are now being purchased because they're contaminated. There were health impacts. We know that. Airborne impacts, 6 creeks, 3 on 2 different trees feeding into the Ohio River were contaminated. Fish kills were in the 50,000 range, animals in the 85 or 7,500 range. We know impacts to humans. No one died yet. Because of maintenance of the transporting vehicle, or lack thereof, we have an incident that now has affected a watershed going into the Ohio River. It has subsoil, soil and subsoil impacts. It has groundwater impacts, surface water runoff issues, and people are out of their homes. They're displaced. Simply because someone in some railroad maintenance facility did not look at the bearings and the undercarriage of the tanker that held the liquids that we're talking about. Those are simple instances. I'll leave this open to your questions, but those are simple instances that have created significant problems, all of which were easily removed from consideration with a little attention to practice. One last thing I would say is buildings that are built today, like the office building I talked about at the beginning, are oftentimes now subject to what's called fire pre-planning. Essentially, the building is actually put into a CAD program. The engineering students would appreciate this. All the entry points, exit points, sprinkler points, water access points, the processes going in the building, and any particular hazards associated with them are dictated into this particular piece of software. That file is then shipped directly to the fire company immediately upon response, as soon as they start responding. So those are steps that are on the forefront of preventing these kinds of things from happening. But the simple standard operating procedure observations, what we really need to be focused on to get to that point. Thank you very much. Any questions? Thank you.
Thank you, sir, for your session, which was very much informative. May I now introduce Ms. Catherine Werner, next speaker of the day. With over 30 years of environmental, health, safety and sustainability experience in Fortune 500 manufacturing and consulting, Ms. Catherine owns and serves as a principal of ESG EHS Services LLC. Her company provides resources to business, government and non-profit sectors to meet hard to achieve environment, social and governance goals. Ms. Werner began her career in consulting, working for companies like Bose Allen and Hamilton and Radiant Corporation. She developed Superfund policy in support of EPA in Washington, D.C. After serving for GE for around 23 years, she served as Vice President of Sustainable Business Operations for Hobbs and Associates. Ms. Werner maintains both her certified hazardous material manager and certified safety professional credentials and is a member of American Society of Heating, Refrigerating and Air Conditioning Engineers. She resides in Louisville, Kentucky with a family. I request Ms. Catherine Werner on stage, please.
Good morning. Is it still morning? Good morning. So I have a presentation planned for you today, and that presentation is on chemical site safety and security. I've been giving a lot of thought to chemical site safety and security, as I'm sure you have too, today, with the incident that we had in India at the fireworks manufacturing site in Hazardous. And I'm going to talk in the formal presentation about a couple things, but I have a request. Can everyone hear my request? I have a request for you, and it's a request at lunch. I know I'm between you and lunch. I understand. I am between you and lunch. So I will be very succinct. Here is my request for you. That at lunch, does anybody have a telephone in here? A phone? Or raise your hand if you have a cell phone. Oh, look at that. Okay, good. Then you likely have access to an article giving you more information about what happened in Hazardous. At lunch, I would ask that you read that article about what happened in Hazardous, because we will ask you to think about why you think this happened. This is a class on hazardous materials management, right? Okay. It's also a class about leadership. It's a class about quality. It's a class about keeping our communities safe and the reputations of our companies pure. And this story holds a lot of lessons. It's not a story about a long time ago. It's a story about this week. It's a story about people's families. They went to work and some didn't come home. And so I ask you to read that article about this incident so that we can talk more about that this afternoon. We've been reading about it. All the facts are not known. So there are many perspectives on what happened, and that's how it works. Early in an incident, we don't know all the information. So I just want to challenge you to read. Take time just to, maybe not now, after this presentation, take time to read about that so we can talk in some more detail.
And potentially we might like some volunteers to help us have that conversation later this afternoon. Okay. All right, I'm swapping over to the podium here. Let's see what we can do. So now I have a number of slides that look like traditional PowerPoint slides. And what you're going to hear today is, all right, I had an extra cup of coffee, so I'm switching back to the mic so I can walk around a little bit. But what I'd like to say about these slides is initially when they were prepared, we wanted to talk about dual-use chemicals. Many chemicals can be used for wonderful purposes for humanity. But in the wrong hands, think about toxic terrorists, okay? It's not a topic we like to talk about. It's, for me personally, my orientation is that the people in the world are good people, and we all go to work to do a good job and come home at the end of the day and be with our friends and family and pursue our hobbies, etc. But there are bad people in the world who have intent to harm others. And when we talk about chemicals and site safety and security, it's important to recognize where you store and have these chemicals that it's possible for bad people in the world to try to target your site to do bad things with the chemicals. So in my mind, at the beginning of this talk and when I was preparing last week and the week before to come and be with you, I was thinking there are really a couple situations where we have failures in these systems. And in my mind, before I was here, I was thinking, well, certainly we have unexplained weather incidents that can cause terrible things in facilities with stored chemicals. And we do our best to predict 100-year floods. We do our best to predict weather patterns to avoid these situations and prepare for them and build our facilities to withstand structures of, earthquakes, winds, all the things that can happen by nature, right? And then we have the incidents. Does anybody, has anyone taken Six Sigma? Does anybody know Six Sigma? The quality term? It is a methodology to eliminate error in your process. And humans, if you only rely on the human for process, a human operates at about 3 sigma without additional process help. We know people make mistakes, right? It happens, not with intent. I can be a great person, but I might still make a mistake. I might follow the map incorrectly and show up at the wrong location. Whatever it is, right? Sometimes we make mistakes. So I was thinking about errors mostly in terms of honest mistakes, I'll say, that people make, and then those with intent. Someone intent on doing harm, like a terrorist. Okay, what I've come to think about a little bit more is that there's a third category. And this third category, I think, is the most important one for people in this room to think about. As you think about your ethics and what you believe in and who you stand for and who you are, as you go to work for companies, it's very important to find your voice in situations, because you may be an auditor and you may find things that are wrong and you may report those things and you may expect things to be done about them. Do not be shy about going in again and saying, did we get that fixed? And going in again and saying, did we get that fixed? And again, did we get that fixed? Because that job might save somebody's life. And there's a situation, and I'm going to show you some other examples in the formal slides, but has anybody heard of, it was a dam failure in Brazil. And this dam was owned by the largest mining ore company in the world. Okay, so it's a wealthy company, they do well. Largest mining ore company in the world, called Vale. And in Brazil, January 25th, 2019, a dam made of mining waste, mine tailings, what it's called, mining waste, collapsed and mud flowed into the town, killed over 250 people. And guess what? That wasn't a surprise. That was not a surprise. Because in 2015, the dam auditors started to report that there were weaknesses in the dam and that it needed corrections. And the auditors are filing their reports. And I pulled something up today about that. So that incident happened January 25th, 2019. In 2021, the 16 top executives were brought up on murder charges. Not just bad management. They were brought up on intentional homicide charges because it was known what happened. So the SEC published an article that I have on my phone, which is why I have my phone with me on the stage. The U.S. Securities and Exchange Commission claims that beginning in 2016, they manipulated multiple dam safety audits, obtained numerous fraudulent stability certificates, and regularly misled local governments, communities, and investors about the safety of the Brumadinho Dam through its environmental, social, governance disclosures. So I'm going to summarize that in they lied in their formal reports. Okay? So that's a bottom line, and they're being held accountable now. But many years later and many lives lost. Too late. In fact, in Brumadinho, Vail, this company, installed alarms to let the communities know if there was a dam breach. Guess what happened? January 25th, the dam broke, and those alarms didn't work. You know why? Nobody tested them. Just like we talked about with emergency response preparedness, you have to test the alarms. If you wait till the day of an emergency and they don't work, it's too late, right? So these are the things, when we all talk about preparation and thinking about what emergencies could happen, these aren't the ones you know are going to happen. These are the ones that may happen. This is why these drills are important, and this is why it's important to think about these things. So, if I had to end my talk now, I would stop there. I do have a little bit more to share with you, and I'm happy to keep going if you all would like me to. Yes? You'd like me to keep going with the information? Okay. All right, I've waited so long on the slides, they may not forward. Let's see. I might need my favorite computer science student to come back up and help me. Is Robbie around? Oh, thank you. Oh, good. Okay. Well, do we have a power switch cord? All right, just a little low. Hey, look at that. Okay. All right, so there is always a natural conflict, sometimes between chemical safety and security. When I give you a couple examples, you know what I mean, okay? Chemical safety, we're trying to, keep the chemicals safe, and security, you're trying to protect against deliberate harm and action, okay? So here's an example for you, okay? This is an emergency exit door, and it's a perfect example of the natural push and pull between safety and security, right? So safety, you want people to be able to get out of the building in an emergency, right? And security, you want to keep all your materials in the building safe. And so it's always a constant struggle to balance those competing interests, right? I've already talked about a number of reasons why you need to worry about chemical safety. There are some bad people in the world, and there's some examples of terrorist organizations that have gone into normally run companies and taken over their chemicals for bad use in the world, and so we'll go over a couple of those examples. But this is one of the reasons that site security is so important, particularly if you're storing large quantities of hazardous materials and chemicals. So, like we said, unfortunately there are some bad people in the world, but that's true, and there are a lot of books about it. And there's a pretty long history of people using chemicals for harm. And so, as much as I like to be optimistic about humanity, I think there's some reality that one has to have a look at to make sure you keep things safe. Obviously, as you think about chemicals, you want them to be maintained in a way where you have control over those chemicals, you know how they're going to be used. And what that means is understanding, keeping very close tabs on your inventory. If you have hazardous materials, you need to know what's coming in, what's going out, how it's used. You need to account for every ounce and bit of that material. And then you start talking about radioactive material, you know, some of the things that Richard was talking about earlier today, and that's a whole different level of accounting that you need to maintain. So some real life scenarios, you know, not every scenario is intentional. This is a USA, Texas incident that happened in 2023. Okay, thought I'd give you one from home. Look, these incidents happen all the time. What's the most important thing to know when you read something about an incident? How do you prevent it from happening again? Okay, that's it. You're reading and you're thinking about your business, you're thinking about your campus, and you say, I never want that to happen here. What can I learn to prevent that from happening in my home, at my site, on my highways? So here, this is Deer Park, Texas. This is a Shell refinery site, and 9 employees were hospitalized. No one passed away at this location. Surface water contamination, wastewater discharge to the Houston shipping channel, so that's pretty significant. That's a big body of water there. Extensive unpermitted air emissions, which you can see here, and you can see on the slide that Bob shared earlier about the derailment in Ohio. A lot of air emissions, burned for a couple days, he said, right? So, as did this one. Relatively speaking, $1 million damages lawsuit's pretty small. That Vail Dam failure that I was talking about earlier, they're paying victims over $7 billion with a B. Big money. So unfortunately, this is an example where there was a sarin attack, and it was by a terrorist group. And you can see this was a long time ago in the mid-90s. And this group, unfortunately, took from some universities who were doing research some of these elements that can poison people, and they use them for harm in transportation. That's okay. We're just having a little power outage here with the computer, so we're gonna roll on. And it's like we were saying, there are several other examples that I have that we can roll through. But what you want to consider is when you do your chemical inventory for your site or for your campus, I'm sure you've got a chemical inventory. You need to know where you have your large chemicals stored. And what I would say is think about where you live and what businesses are near you, and think about what chemicals are stored near where you live. And look them up. You all are smart, you've got the internet. Look them up. Is there anything there that can explode? What's the blast radius? Are you in it? What do you need to know about? There's a tool that is free from the Environmental Protection Agency. It's called Aloha. Aloha, you can put in your parameters for what chemicals you have, and it can model out for you what the blast radius is. So I mentioned the other day that we had a fire, Lois and I talked about it. A GE burned down a 1 million square foot building. What we didn't talk about was that there was a tank of a substance called cyclopentane, highly explosive. And we use it to make refrigerant foam to insulate the refrigerators. That tank was located very close to Building 6 that we talked about. In fact, we made the decision to let the building burn and have all of our focus on making sure the fire did not come close to that tank. The blast radius for that tank, which we had modeled out, completely blew up the building next to it, the one next to that, and damaged structurally the one next to that. These are other 1 million square foot buildings adjacent to the tank. It also went all the way over to the FedEx facility that was next door. They were aware of this. But it can have long-standing implications. But knowing all of that risk information before this fire happened was important. And then you look at immediate things. Which way is the wind blowing? Which way is the fire moving? Where are our plastics stored in that building? Because we know that's going to be a particularly hot part of the fire. How close is that to the cyclopentane tank? We even thought about emptying out the tank. Like, could we bring in another tank truck to take all of that material out to reduce our risk? Ultimately, we decided that the volatility may not be a good idea since the wind was a little variable. We decided not to do that and the fire was large. But these are all factors to consider before you have an incident. Oh boy, look at that. Okay. Again, there's some other incidents about bad people doing bad things all over the world. And I think, again, the lessons to be learned are these risks, in many cases, like you see the last part of the slide, it says chlorine was first used in World War I as a chemical weapon. These are not new hazards. But unfortunately, the bad guys can be creative. And while they're not new hazards, they can be used in new ways to create new risks and new targets for all of us. So again, back to dual use awareness. When you're doing your chemical inventory on your site, it's a good idea to go through and understand what you have, how it could be used for good or for bad, and then how to keep it secure. Limiting access to the facilities obviously is very important. Making sure your people are trained, those who do have access, also important. Again, I'm going through the slides really so you can come back and reference them again. I've really said what I thought was most important already in this talk, and there are a couple other things that we can go through as far as how to prevent and minimize the impacts of these types of incidents. Understanding what you have is first and foremost. How much of it do you have? When are you most vulnerable? Kendra said the unloading process is one of the most vulnerable times, and that was certainly true for cyclopentane. The times that we were loading into that tank were some of the riskier times when we were handling that chemical. Once it's in the tank and plugged up and hooked back up to the process, we felt good about that. But loading and unloading was a risk area. We've heard a lot about hierarchy of controls where you do have hazardous chemicals that are dual use chemicals. Is there anything you can do to substitute those out, right? Use something less hazardous to still meet your purpose. And again, there are a lot of good practices in here that you can look at. And what I might recommend is when you read the HARDA article about what happened at the fireworks site, come back to this presentation after and think about it again through a different lens. Have a look again afterwards and think about all these minimization ideas in here and how could any of these be used in that situation. Much of this we have gone over before about chemical safety and chemical properties. So I will not repeat that information for you again today. Setting priorities. Who sets priorities for an organization? Who sets the vision? Who sets the values? This is actually a question I'd like an answer to. I'll ask it again, just, because now you know I'm asking a question, so I'm going to ask it again. Who in an organization sets the vision, the goals, and the values? Who does that? Anyone? The CEO, absolutely. The leader of the company, and those who sit in the C-suite. Yes, thank you. Even though you're nervous. Okay. But, no, I appreciate it. Okay, so, why am I asking that? Because the CEO may set the vision, and he or she may not come to your facility for a long time. So who is then responsible for implementing that vision and implementing the values and the ethics that are conveyed by the CEO? It is every person in this room that sets foot on that campus, whether a guest, a contractor, or an employee. And everyone needs to understand it and consistently be able to say what our goals are, what the vision is, and what the ethics are of the company. And if you feel uncomfortable, you need to raise your hand and speak up. And that's one of the most important ways you can prevent bad things from happening. Almost in every situation, there is some warning sign. There's a warning sign. And if you're listening and you feel it here, you need to probably say something. If you walk by and somebody you don't usually see is there, they don't have a badge on, hey, at least ask them, can I help you? How can I help you? Speaking up and not saying it's, somebody else's job, somebody else will think about that, is so important. And you can prevent very significant incidents from happening by speaking up and standing up for the goals and ethics of your organization. And you can avoid the miserly person with malintent. So controlled substances, clearly locking them up is important and keeping them secure. Again, managing the inventory, having a system to do that, very important. We've talked a lot about risk management. I'm not going to revisit that, but I would encourage you to have a look at Stephen's report again on risk management, likelihood and severity of incidents. Super important. Where are you vulnerable? This is important. So as you think about your risks and you think about what's red, remember how I said when we did our risk assessment, we said, a huge fire is very unlikely. And it happened. So thinking about your vulnerabilities, and remember what I said the other day, that's so important. It is not if we have an incident, it is when we have an incident. Because we will all have incidents. So when you have one, what will it be? And how are you prepared to respond? Today, not after. After the incident, there's lots of money to fix things. How are you spending your money and how are you budgeting today to prevent the incident, not spend all the money after? Does it help those families in Vail, down in Brazil, that Vail is spending $7 billion after 250 of their family members have passed and their village is destroyed? That's not super helpful. What if they spent half of that up front and they never had the dam failure? That might be better, right? So these are decisions that you will make as leaders, and these are examples you can draw on to make your point stronger. So yes, there's some good models in here about evaluating systems, the cost and impact of delayed maintenance, deferred maintenance, and when and how to spend capital investments. You all are important. If you're a chemical professional, a chemical educator, engineering educator, business manager, and educator, you have great power in your hands to deliver and reinforce the optimism and ethics that we all have in this field. And with that, I thank you, and I'm happy to entertain maybe one question since lunch is next. So maybe just one, and maybe there are none since lunch is next. Thank you all very much. Please do your homework and read that article over lunch. Thank you.
Thank you, Ms. Warner, for your valuable inputs. It's time to have a lunch break. Request everyone to assemble back here at 1 p.m. today. I request all the female participants to have your lunch in main block 314 seminar hall. I repeat, I request all the female participants to go and have your lunch in 314 seminar hall. After the lunch, please come back here. We will have an afternoon session and followed by a cultural event.